Hi everyone, thanks for joining us today. My name is Saliha Sally and I'll be presenting on behalf of my co-authors Nick and Katarina, and today we'll be talking about modeling verbal morphology in NEN. I'll be walking you guys through an overview of our paper, starting with the NEN language and more specifically its verbal morphology. We'll be talking about the experimental setup, the data set and the models we've chosen to use, and then we'll be delving into the experiments we ran, starting with experiment 1, training size and error analysis, then to experiment 2, where we examine the effects of training data composition, and lastly, the syncretism tests, where we test the models on an unseen form. The NEN language is spoken in Papua New Guinea, specifically the southern part, so the belly of the bird, and in the village of Bamadaban, which has about 300 to 400 inhabitants. We've chosen specifically to model verbal morphology because the verbs are the most complex word class in the language. The verbs can be further categorized into 3 specific classes. And these are ambifixing, which is the maximal case, and that's just because it utilizes both prefixes and suffixes, and this yields a full combinatorics of up to 1,740 unique forms for one stem. And then we have the middle verbs, which are also ambifixing, but the prefixal slot is restricted. So they only have 3 prefixes available to them, which make them, in a sense, a subset of the ambifixing verb. And lastly, we have prefixing verbs, which only utilize prefixes and have their own separate closed paradigms, and these are basically determined through semantics. So the most common prefixing verb is the copula. Here we show an overview of the verbal template. So you can see it's split into prefix, stem, and suffix. Within the prefix, we have 3 slots. So the first one obligatory, so the undergoer person number. The second optional, so it's a directional, whether you're coming, for instance, towards or away, or a neutral semantic. The third, the future imperative, which is a specific TAM or tense aspect mood category. Within the stem, in our case, we're mainly focusing on just the root. And within the suffix, we make a split between thematic and dissonance. So the thematic marks the subject as either dual or non-dual, and also has to agree with the TAM category. And the dissonance further distinguishes the actor or subject's person number, whether it's singular, dual, or plural, and has to, of course, agree with the TAM category. We can't really talk about NEN verbal morphology without mentioning distributed exponents. Distributed exponents is essentially a many-to-one mapping of form to meaning. So grammatical meaning is distributed across smaller pieces of the word. In the example we have here, no one marker marks the actor or the subject as a singular person. We have the thematic t in green to mark the subject as non-dual, and the dissonant in orange air to further resolve it as a second or third singular person. This sometimes means that we actually have a non-monotonic passing for our verbs, because we can actually have multiple meanings of either certain prefixes that require the suffix to be resolved. For our experimental setup, we decided to follow the sigmorphon shared task for reinflection. So our data set was made up of triplets, which consisted of lemma, grammatical tags, and the reinflected form. We utilized the 2 top-performing neural network models from the 2017 shared task, which made distinction for the low and medium resource settings. So the 2 models we decided to use were the hard monotonic attention by Aharoni and Goldberg, and the neural transition-based model by Makarov and Clementine. The dataset we use is derived from the NEN naturalistic corpus, which is comprised of material ranging from biographical interviews to folk stories. So the total corpus is approximately 30,000 words, and in 2017 for my master's thesis I made a sub-corpus of only the verbs. which is about 6,000 verb tokens. I have hand glossed each one of these, and that makes up about 2,231 inflected forms, and of those 274 are unique lexemes. For our first experiment, we follow in the footsteps of the 2017 Sigmoid-Fontaine task, where we examine the effects of training size on the model performance. We extend this by further exploring the differences between sampling methods, where we contrast the difference between random sampling and Zipf sampling. So for each resource setting, we follow their definitions, which goes for high, medium, and low, go as 10,000, 1,000, and 100. We've introduced all, which is basically the maximum available for our corpus, which was 1,931. So to achieve the high resource setting, we've utilized the 2019 hallucination method. Rather surprisingly, we found that where the random sampling was viable, it outperformed the Zipf counterpart. We think this is basically because of the fact that prefixing verbs, in particular the copular verb, are more frequent in the natural corpus than the ambifixing verbs. In the second half of our first experiment, we basically analysed the errors produced by the models and categorised them according to the taxonomy laid out by Gorman et al. In 2019. We've identified 4 types of errors that commonly occur. The most common of all, the allomorphy, which is basically a misapplication of morphophonological rules or feature category mappings. So an example of this might be an absence of vowel harmony in the inflected form produced. The second is a category we introduce, free variation, and that's basically a consequence of the fact that our corpus is naturalistic. So you might have interspeaker variation of various forms. So more than one acceptable form may exist. The third category is the target error, which basically means that we have mistakes in the gold standard. So in this daunting table below, you can see that in the target row, each category basically has an 8, and that's just because the test file was the same for all, so you would expect that to be the same. And the last category is the stem category. So basically this comprised of non-stems, so stems that were made up that don't adhere to NEN phonology, or basically remapping of a seen but irrelevant stem. In our second experiment, we explored the effects of the composition of the training data, and this question arose from the differences we saw between the random and Zipf sampling. So we created training sets according to verb type. So we had prefixing only, middle only, and ambifixing only, and then the combinations of each. So prefixing middle, prefixing ambifixing, middle ambifixing, and then one category which had an equal distribution of prefixing, middle, and ambifixing. Each set is made up of 386 instances, and this is just because that was the maximum amount of prefixing verbs we had available to us. So the test set is made up of 34 ambifixing, 33 prefixing, and 33 middle verbs. Unsurprisingly, we see that the set that has ambifixing only performs best with ambifixing verbs and very poorly on middle and prefixing. And the same is true for middle and prefixing, so they all perform best for the verbs that they've seen. More interestingly, we see that when we actually start mixing, even between ambifixing and prefixing, we see that the prefixing actually still performs better. It performs better on the prefixing verbs, and we think this is basically just because the prefixing paradigm is way smaller than the ambifixing. So when you split the type of verb into 2, so in this case the system only gets to see 193 instances of ambifixing. This is nowhere near enough to actually be able to capture those patterns. And then when we go to ambifixing and middle, we see some transferability between the two, but again, the middle verb actually performs better. Rather, I think the most linguistically interesting one is the middle and prefixing, and this is because from a principal parts point of view, if you actually understand the prefixing paradigm and the middle paradigm, then you should be able to actually develop the ambifixing. In this case, we see very little of that, and that is likely due to the fact that we have a middle-only tag. So it doesn't really allow for that generalization to happen. In the last set, we basically, where we have an equal amount of each type of verb, we basically see a further divide between the two models. So we see that the Makarov and Clementine actually performs a lot better across the three. Our last experiment was about testing syncretism. So our research question was whether the models actually infer properties of the language which are not directly annotated in the data. So in the NEN language, almost all TAM categories exhibit syncretism across the second and third singular actor. And there's only one instance where this breaks, and that's the past perfective slot, where there's distinct forms for the second and third person numbers. So for our experiment, what we did was basically remove the instances of the second singular past perfective in the corpus, which was only 2 instances, and made a test set of 100 instances, and therefore had to supplement the 98 from the NEN dictionary to test what the model would produce on this unseen form. Would it actually predict the form to be syncretic with the third singular, which is seen across all the other TAM categories? So the answer we got was a resounding yes. The Aharonian Gold model, although incorrectly, but still rather fascinatingly, predicts 81 out of the 100 test forms as the third singular. Similarly, the Makarov and Clementine model predicts basically the same thing 90 out of the 100 times. And the remaining times out of the 100 were either just completely incorrect TAM categories or other types of errors. But from this, we can see that these models are actually picking up some of the more subtle patterns within the data we train with. In our paper, we show the first neural network application for the NEN language, and more generally the Papuan language family as far as we know, which is an important point because a lot of recent rhetoric in NLP has been about including more linguistically diverse languages. We don't stop at just modeling the morphology, we also categorize the errors produced, and we added a new category, free variation, that arises from a naturalistic corpus, which is going to be more common for those doing language documentation. We explore the verb type composition effects in training data and the consequent generalizations learned, and that's just trying to understand the effects of training data and what is actually being learned. We show that both models learn implicit relationships within the data source. So we show that even though we're not explicit about syncretism, the model is picking up on this behavior, which kind of leads us to actually think a little more carefully about the training data we provide for training such models. Thank you for listening, and I hope you enjoyed it.